All right, so kind of continuing on now to section 20, right? So our section 20, I'm just kind of looking at learn a little bit what's going through since I was a little caught off guard. That's not all the stuff that I was talking about was in there, but for section 18. So, okay, so yeah, we'll talk about, let's hear it. In learn, it says experimental design, p-values, null hypothesis, effect size, conducting t-tests, one sample t-test, two sample t-test, type 1, type 2 errors, and all that just fun stuff. Okay, so I kind of split this up. Is this what I wanted to talk about? Yeah, so I'm actually going to go into the intro, which is like the first notebook. I should probably split this out since it's now a separate item. But I wanted to mention very quickly about, maybe it's not in here anymore. Is it? Did I take it out? I did take it out. Okay, never mind. Good. It is taken out. I think I left it into, sorry, I'm just kind of organizing my thoughts internally. All right, so I want to talk about this one. I guess we'll just go right into experimental design. Never mind. I'm going to take it back then. All right, so we'll go into experimental design. So you can see all this great stuff that we're going to talk about for the next, not just today, but also next week too. So first one we're going to talk about is our statistical test itself. So good, that's already open. So there's a few things that we're going to talk about that I normally would talk about in the first statistical distributions, but it kind of got moved around a little bit. So kind of bear with me, there's some missing parts, but I'll kind of go over them. But the first thing basically is that we're going to talk about statistical tests or hypothesis testing, right? So there's some things that we should know about. This is kind of made more of review, but we're basically denoting these as our null hypothesis. So usually know it's H0, H sub 0, H O sometimes our null hypothesis. Basically, this is the thing that if we had our experiment, we assume that our, what's it called? How do I say this? We assume that there's no difference between an experimental group and like our control group. So you can think of it like if we were to do this like treatment. So sometimes you can think like, you know, in medical field, but this can also be considered like, oh, if we adjust like the color of a screen for a website, right? That would be considered a treatment. Is that the change that we made has no effect. The null hypothesis, null meaning nothing, right? So it has no actual effect. That's what we mean by the null hypothesis. Okay, the alternative hypothesis, which is denoted a couple ways. I've seen it denoted both as HA and H1, kind of going off of the H0. I've seen both ways. I don't think there's any true preference. But this is assuming the opposite thing, where this hypothesis assumes that there is a difference between the experimental group. The treatment had an effect. So what we changed did actually have an effect. That's essentially what the alternative hypothesis, and they basically are in conflict with each other. So essentially what we want to do eventually is basically say, we either want to fail to, or we want to reject the null hypothesis. So we reject the fact that the null hypothesis is true, right? So that means it's like, oh, we say, oh, we assume the null hypothesis being like, oh, there's no effect. And it's like, oh no, we can't reject it. There was an effect in there, or at least we've seen an effect. The opposite, if we fail to reject, or if we reject the null hypothesis, the opposite is we fail to reject the null hypothesis, which is kind of weird. So the way that phrasing is going through, but I'll say definitely approach it that way. So I'm gonna give a little warning here. Oh wait, no, I don't have to say it here. All right, I'll say it right here. Is that you will hear people say, accept the null hypothesis, or I'm sorry, accept the null hypothesis or accept the alternative hypothesis. Don't be those people. Those people are wrong. No, but they're definitely like, I mean, in reality, does it really matter? No, but I will tell you is that people will kind of give a little like, you don't really know what you're talking about, do you? Kind of deal when you say accept the null hypothesis or accept the alternative hypothesis. So the real reason why we do this is because we really are, in a lot of ways, are assuming the null hypothesis. And when we reject the null hypothesis, it means like, oh, there's evidence to say that the null hypothesis is not true. But when we say we fail to reject the null hypothesis, we don't accept the null hypothesis because there's a chance that maybe there was some other random effect, or there was a random effect just by pure chance. So we fail to reject, not that we accept. The way I kind of say this is like in science, in a lot of ways, you're never proving anything in science. In a lot of ways, you're always disproving things in science. So essentially that's what we're doing here. And that's kind of the terminology and the mindset to approach these things in, is that we're never trying to prove it. We're more like trying to disprove things. And what's left over is likely the true story, okay? I'm realizing I am missing something on here. We'll maybe go back to it. But a quick warning is that once we accept, like, accept that we're doing these kind of tests, if we reject or fail to reject the null hypothesis, right, it does not say how strong of an effect there is. It's just saying that it was significant, meaning that statistically, we'll say it was statistically significant. But the opposite is, even though it's statistically significant, doesn't mean it's practically significant. Okay, so a good example of this, we'll talk about this for effect size. So a good example of this, I'm going to kind of skip before I explain effect size, is if you imagine like if being a male or female for a certain species has an effect on the size of the animal, right? So for example, I think I've seen an example of this, like elephant seals. Elephant seals are massively different in size if you're a male or female. Males are much larger than the females, okay? However, male and female dogs, yes, there is a difference. Like there is a statistically significant difference between the size of the dog, but the effect is relatively small compared to what it is with an elephant seal. So that's essentially what you're going to talk about, right? Is there any practical significance? There could be, but depending on the situation, it might not actually be a practical difference between the two. Maybe if you're giving, maybe if you're just trying to see like how much dogs weigh in general, like maybe there's certain medicines they have to take into account the weight, but maybe that's not a big enough difference for it to actually make a difference in the amount of medicine that you give for a dog, because maybe it's off by like a couple pounds, and maybe a couple pounds is not significant enough to warrant a different medicine or a different dosage of medicine. So that's the kind of way to approach this. Okay, so this leads into, like I said, like was there an effect? So we can conduct experiments and figure out if there actually was a difference. So one thing we want to do is use p-values. So p-values, and I'm going to reference something that I would have shown you guys, but I hadn't shown you guys yet, is puppy p-values, which is a really great kind of little article written by, I don't remember her name, but she does a great job explaining p-values with puppies, of course, because why not, right? And what's nice is if you don't like to read this article, there's also a nice little video that she basically does the same thing. But I would suggest, there's a video here. Where is it? Oh, maybe it's not here. But she does have also a video here. I'll make sure it's linked over where she explains the same concept. But I'm just going to kind of summarize what she's going to say. What she says in this article is that p-values in a lot of ways are just telling you how strange something is. So a low p-value basically means like the probability of this actually happening. And it's kind of saying like it's measuring how strange this part is. So she gives the scenarios like, imagine you come home and you have your puppy, right, at your house, and you come in and you see a trash can over your puppy's head, right? And trash is sprayed out everywhere, okay? There's some possibilities that could happen. One, the puppy got in the trash can and started tearing up everything. Okay, that's one explanation. But the other explanation is that someone broke into your house, took the trash can, sprayed it out to frame the puppy, and then put the trash can on the puppy's head right as you were coming in and left, right? Technically possible, entirely possible, right? The likelihood of that happening seems relatively small, right? There's a lot of things going against this, concept. And so we would assign basically, in the sense like, well, like our p-value is basically saying, well, what situation is more likely? Is it more likely that the puppy caused this mess, or was it more likely that this kind of scenario with the person breaking into the house is more likely? And essentially what we do, we basically measure a threshold, and this is where we'll talk about our critical values, but basically measure a threshold and say, how much weirdness are we allowing us to accept until we accept that, we fail to reject our null hypothesis. And fail to reject our null hypothesis basically means that we think that it's something alternative to like just the puppy, breaking into the trash can. So like, how weird do things have to be? Like, for example, like, okay, like that doesn't seem like there's too much weirdness to begin with, but if you see footprints in like the kitchen, you're like, that's kind of weird. So you're basically your likelihood now that p-value is increasing in the sense where you're starting to not fail that rejection, right? And say, oh, the window's open too. Oh, you see someone running away from the window. It's like, okay, this scenario is getting more and more likely, right? So the point is that basically that p-value is measuring how weird does a scenario have to be until you accept, well, not accept, but you fail to reject the null hypothesis. Basically, you start thinking of other possibilities beyond the null hypothesis. Okay, so I kind of like that scenario. I think it's a kind of good idea. Also, I like when she talks about in her video, she just mentions like, the p-value is also like, this is a very strange way to kind of measure things. And that's because it's not really intuitive. So if you ever feel like p-value is like, I don't quite understand what p-value is, that's because it's not supposed to be like super like intuitive by itself. It's to help us measure things out. But when we get a hypothesis, right, we can measure something like the p-value, right? We can calculate this p-value. And then from this p-value, we basically say a threshold, which is our critical value, and say how weird can things get before we reject the null hypothesis. So you can think of like, usually we'll call the critical value as alpha. Usually alpha is set as 0.05. I think the curriculum even mentions this as 0.05. And basically it's saying, when do we say it's significant enough? This little comic is from XKCD. So, which you'll see a bunch of comments from XKCD when I do these things. But if 0.05 is our cutoff, anything below 0.05 is saying that's really, really unlikely. So like you can imagine 1% of the time this would happen just out of pure chance. It's really unlikely. We might reject the null hypothesis and say, okay, that means likely the alternative hypothesis instead. And I just like kind of like this little graphic is that usually we're like, oh, like, this is kind of like not significant would be higher p-values. And then as we get lower, it's like, oh, like really close to a significant value. And then there's this joke. It's like, well, what happens if you're exactly 0.05? You're like, like, do you accept it? Do you reject it kind of deal? So kind of redoing calculations. And this actually leads into a little bit of p-hacking stuff too, where essentially you adjust this until it works out fine, right? So a quick warning. Oh, this is one of my little favorite stories. There's a chocolate study that was conducted by John Bohannon. I don't know. He wrote this. Basically, he was going to create this study, and basically the whole thing. It's actually this great article from Gizmodo. Actually, kind of explains this whole process. What happened? Essentially, what he did. He said, "I'm going to make a study that will be scientifically correct, but will not be true. That will get the results that are not true." And essentially what he did, he measured many, many different aspects with a small number of participants with a lot of conflicting factors. And eventually what he found is that chocolate causes weight loss. And the funny thing is that he even said publicly before he actually put the study in, he said, this will not be a true study. Like this will not be good, but it will get published and it will be taken over by media. And it was actually published on a journal, maybe not the best scientific journal, but like it was published in a scientific journal. Well, some, people from the media, like reporters and stuff, found it and reported off, say, oh, the study shows that chocolate causes weight loss. Because I mean, who doesn't want to just eat more chocolate to lose weight, right? So essentially it was a really cool, title. And essentially it took off and it was being reported all over the place. And I guarantee that there are probably still people who probably use this study or some reference to the study in some way that chocolate does cause weight loss or something like that. I have heard it like recently in the past couple of years where someone had mentioned this. I'm like, oh, that's a fun little story. Like and then they weren't my friend anymore. But anyway, it's kind of an interesting cautionary tale. And basically it shows a lot of ways how you can do correct, results, and you will get results that are significant. The p-values were lower than the alpha value and stuff like this, but the method of it actually being conducted was improper. And that's an important aspect when I say think about statistics is think about how you're doing the study or whatever you're doing. It doesn't have to be a study, right? Basically the data collection. How is that data collection being done? And that will affect, whether or not you should really be able to interpret it in certain ways. You might need to adjust your alpha value depending. Okay. So kind of a quick moral thing. Again, another little comment from XKCD is that one thing too is like in this ordeal, he talks about measuring multiple different things. If you measure multiple things that have no effect, right? So imagine like you measured all these things, they actually don't have any effect on people's weight loss, right? Well, the problem is if you measure enough of them, eventually you'll find something that will have an effect, right? By pure chance. And you'd expect that because there's a 5% chance that basically there's a false positive, right? And so there's a little comment right here from XKCD where he basically goes to, they're looking for jelly beans. They say, do jelly beans cause acne? So they basically do the study with jelly beans and they find with a p-value greater than 0.05, which is all proper so far, right? It does not occur, right? There was no link that they could find. They failed to reject the null hypothesis, right? Cool, right? And it's like, oh wait, it's maybe a certain color. Well, then what they do the same study over and over for every color. So they try it with purple jelly beans, they try it with brown jelly beans, try it with pink jelly beans, blue jelly beans, all this stuff. You see P greater than 0.5, P 0 greater than 5. And then they try it with green jelly beans and see a p-value less than 0.05. And you're like, oh, cool. Like that means there's an effect here. The fun thing is that I think Random Monroe is pretty smart here. If you count how many possibilities are here, there are 20 possibilities and a 5% chance, 1 out of 20 is probably going to have a false positive in here. So it actually kind of shows a little bit like, oh, if you do multiple comparisons, eventually one of them is going to have this significant effect. And of course, then the news says, oh, that means, there's actual effect. And the funny thing is that this probably would be, this could possibly be published in the scientific journal and stuff like that. So we're not really talking about science in particular. Like, as data scientists, we're not talking about pure science by itself. We're talking about also business case, but this is a trap that you can easily find yourself in and not realize until it's, essentially say, oh, hey, we did find an effect, but in reality, it's just out of pure chance. So multiple comparisons is something we'll talk about later this week as well. But I just share this little comic. Okay. So any quick questions about p-values, critical values, how hypothesis testing, between the difference between the null hypothesis and alternative hypothesis? No? Okay. And note that this null hypothesis and alternative hypothesis tend to be complementary. So that means like there's only two possibilities. It's either the null hypothesis true or the alternative hypothesis true. There isn't like a between part. So note that that's why when we reject the null hypothesis, we essentially are saying that the alternative hypothesis is likely true because that's the only other option if the null hypothesis is false. Okay, cool. All right. All right. So let's go to our next part. I have so many different, I need to order these. I think I need to order these a little bit better so to match with the curriculum, what we're seeing. But we're going to talk about experiment design itself. So, and then we'll do effect size. Oh my gosh, what the heck is Chrome doing now? I had an update and this has thrown me off. Do you guys see that group, right? Like, okay. Yeah, I don't know. I haven't done that before. I'm not sure what caused that. Okay, so we'll go off this. So experimental design, some quick things. I'm not going to go through this in depth, but it's important to understand like what makes a good experiment. So I know a couple people, science background, familiar with the scientific method, at least in concept. I used to teach science lab. We would go to the scientific method and I would tell them, it's not that scientists like have this like a memorized aspect of the scientific method. This is like, they're like gold-plated thing. It's like, this is a general idea of how the scientific method works through, right? So the main thing is that is also really useful for data science is that you want to start off with a question or observation really, right? Our business case, like what is the reason we're looking to explore this, right? And then looking at the background saying, okay, like what thing we usually call this in data science domain knowledge is understanding that background information. Then we want to develop a hypothesis. And this is actually a really good part is that we need to make sure we make it really clear that we have a hypothesis. One danger sometimes people do is they start looking at the data and start going through. It's like, oh wait, what's my hypothesis? And they forget exactly like what was their clear hypothesis. You want to make that as clear as possible. Okay, and then you can actually perform your experiment from there, your analysis, your conclusion. So this is the scientific method, and that's kind of what we're basing this around. Okay, so some things to consider when making a good experiment is that you want to make sure that you're thinking about random trials, you're thinking about control groups, your sample size. A control group, does anyone know what a control group is? When we say like a control? Good. So just kind of reiterate is that our control group basically is something that we are not changing, right? That's kind of like your null hypothesis equivalent. It's like, there's no change in this. Random trials, I think earlier Lauren had mentioned about like if we did this experiment with the little children with different flavors of ice cream, like vanilla or chocolate or whatnot, you'd want to make sure you use random trials, right? Is that you'd want to make it as least amount of bias as possible. And note that this is actually really tough to do sometimes, is that making it truly random is actually a really tough thing to do because you'll always get a little slight bias in the way you're doing things. So if it's not a random trial, just kind of be aware of that too and say, okay, is this random enough for the situation? Note that you don't have to be perfect. If it's not perfect, it doesn't mean that the data is not relevant. It's just that you have to be aware of what are the possible biases and take them into account when you get your results. Your sample size, more people are better, right? So like the more you have in your study or your data set, the better. For data science, usually we like to have these large data, but sometimes for data, you're just not going to have as many just not as big of a sample and everything like that. So note though, we'll talk about this in a little bit for our t-test, is that usually, like, surprisingly, a little over like 30 per sample, or within a sample, is usually good enough to get a decent result. Which still like flabbergasts me that like 30 is like enough to like basically get results. And it basically relies on the fact that you get close to a normal distribution when you have at least 30 people. Okay, and reproducible, basically saying like you can be able to check this again. You don't want to be able, if you can, like try to design an experiment that's going to, when I say experiment, data set, right? Being able to check this again. So one thing that's really tough to do is like if there's one special event and see if that one special event had an effect on like attendance or something like that. That's sometimes tough to do, because if that one special event doesn't ever happen again or something like it or something comparable, it's tough to really make sure that like, was that a fluke or was that actually related to the event itself? So that's where the reproducibility is really useful in that way. I just had someone the other day tell me, he was like, oh, like we have, like we're looking at this data, it's like, you know, it's changed over, you know, we're expecting it to change over from the specific ad that they put in the specific ad. They wanted to see this results, like, oh, do you have data from before? It's like, well, we don't really have data from before. And I'm like, and it's really tough to say if this ad actually caused something or it's just by pure timing. Like it could just be by pure chance that people are going to do it regardless of the ad. So that's what I mean by reproducibility. Okay. So one kind of thing, resource, but it's more like, you know, more entertainment, is healthcare triage on YouTube. It's this great, YouTube channel. They're actually from, I forget, it's, was it John Green and Hank Green? If you guys know the Green brothers, that way. Anyway, they make some really great educational like shows. It's, like educational meaning like relatively like at least high school level, if not higher. But healthcare triage talks a lot about, his name is Aaron Carroll. He talks a lot about like analyses from like about medical and stuff like that. And I think he does a really great job of like showing it, like saying, oh, these are the different papers, talks about meta-analyses and stuff like this. I think if you just want to get something to feel for like, you know, how to kind of approach this and like how these can be useful, I think it's a really useful way to like see like what he talks about, like when experiments are bad, or like, you know, like, oh, like, you know, what things to consider. It definitely, like I like to say, it's like, it's a YouTube show that would never exist. It will never be very popular because it's very like he talks about meta-analyses and like talks about like the significance between like different meta-analyses. I think it's very entertaining. But I'm also a different part of the spectrum in that way. So I don't know, I think check it out. But I think he does a great job talking about these different things. He won't talk about like how to calculate this stuff. I want to make that clear. But I think it shows a little bit of like where this can be applied to. And you can probably catch glimpses of like, you know, oh, this is how I would probably proceed in this way to like do that. And actually driving from the numbers, driving information of saying, oh, is this used? Like, what is this in relation to? Okay. So anyway, I'd throw that in there. All right, so that is experiment design. And I keep going back. I'm gonna see if I can find it real quick, so I won't take too long. There's a part that we skipped over for statistical distribution intro, and I think it's in this one right here. We'll see. Yes, okay, good. So statistical testing. So I'm gonna kind of go back a little bit. I'm sorry, I'm a little jumping around a little bit. Should probably organize this a little bit better. But this is like me introducing statistical testing first. So note that we talked about the z-score before. So this is just the z-score as well. This is the z-statistic. So the z-statistic basically is based around how many standard deviations you are away from the mean. So if you remember, if we calculate the sample mean for itself, right? And then we have the population mean. Note that this mu right here, this population mean, that's not always easy to find, but there's sometimes ways you can kind of reason this out. I'll explain in a second. But basically you're trying to see with the z-statistic saying, okay, how far is my sample mean away from the population mean? And we use our standard deviation here, our sample deviation, right? This sigma divided by square root of n basically is accounting for the fact that if you have more people in your, or say more, I guess, data points within your sample, your standard deviation will actually get smaller, right? Basically, there's less variation as we increase in the size. Basically, those really extreme ones will be less common, and you'll get more that are close to the common actual mean itself. So our standard deviation will actually get smaller as we get, our effective standard deviation will get smaller as we increase the number of participants or number of data points, okay? So You can think of it like our z-score, our z-statistic is really saying how likely is a value from the mean or from the actual population different from our sample. So like how likely, I think this is actually not phrased well, but if you were to imagine like, okay, we took a sample of people, we got a random sample of people and we say, okay, we have this group of people and we're going to compare it with this population. Does this group of people, this sample, actually belong to this population, or is this some weird subset of people? So normally what this would be something like is like you would have like the average reaction time for people in the population, right? And then you would specifically look at like say, okay, let me look at things like I don't know, taxi drivers or like Uber drivers, something like that, right? A very specific group. It could be like athletes, right? Like hockey players or whatever. And you say, okay, let me look at the reaction time for this group and then look at their sample mean, their sample standard deviation, and compare it with what we know as the population mean and say, how different are they? And basically you could say, okay, does this sample right here actually belong with the population? I mean, there's no real difference between any average person, or is there a special case for this case? In this case, you could probably guess as if you have something like hockey players, the reaction times are probably a little bit better than the average person in the population. So there would be a difference versus maybe getting something like an Uber driver. I wouldn't expect there to be a really big difference between reaction times because that's not a huge aspect of their life, even though it probably would be an important aspect, right? But anyway, not to like scare anyone, right? But anyway, the whole point being that you can compare these different groups together and see if there's a match between the two. And that's related to our hypothesis testing. So I'm going to skip z-tests in general in the sense of being like, oh, z-statistic, because we'll talk about statistics in general, like a test statistic. But again, just reiterating hypothesis testing, the null hypothesis, the alternative hypothesis, we always attempt to reject the null hypothesis. We never accept the alternative, right? Or accept the null hypothesis. This thing is really based on what I really want to show you guys. It's based on the normal curve. So what's going to happen here is essentially we'll get like, this is our normal distribution right here. You can imagine this as being like no difference from the mean itself. And then we're going to be somewhere over in this distribution, like we can imagine like, oh, this is where we measured our sample. So sometimes you wouldn't expect it to be exactly spot on to be exactly the sample, what's it called? The population mean, right? You wouldn't expect that to be true. You expect it to be a little bit off just by a pure chance, right? So the thing is like how far off to the right or how far off to the left do we actually say it's too, that's really unlikely or that's kind of weird. Like we wouldn't expect this sample to be so far off to the right. So essentially this red area here is kind of like, you can imagine like the critical zone, like this is made up words, right? But the critical zone, the danger zone being like, oh, this is like the weird zone. Like if it's over in this area, it's too weird for us to say that it doesn't have any effect. So this right here are two different tests. These are both one-tailed tests, which we'll kind of talk a little bit more about. And this is a two-tailed test. And essentially the two-tailed test is saying, is there a difference at all, whether it's smaller or bigger? But one-tailed test can be like if it's less than or is it greater than kind of deal. So these are right tail tests, left tail tests. I never call them those things. These are just usually referenced as one tail, and then you say is it greater or less than. Okay. Usually what I get is people say, should I do a one-tail test or should I do a two-tail test? This is where p-hacking can come in, is that you can get the value here. So imagine like I do this test and I find the value. I'm going to draw this really quickly in blue here. Come on, there we go. Okay, so imagine our value is right here. Let's undo this part. Let's say our value is like right over here, right? So our value is like right here. It's like, it's not quite significant when we consider, is there any difference? I would say, well, let's just look at just it being a one-tail test, right? And it turns out basically this value will be split across 2 points. So you actually need to only, instead of having a value of 0.05, you actually would need a value of like 0.025 because it's split across each part. So it turns out if I redid the test, same exact value, but I said, oh, let me do a one-tail test, it actually would be significant. It would be in that red area. Well, the problem with this is that basically you didn't get the result you wanted. So you adjust, say, well, let me just consider it less than. So it's important to really consider like, you know, what are the things that you really care about? If we're talking about like hockey players, we don't really care about saying we're not thinking that their reaction time is like different. We're just saying, oh, it's probably smaller or faster. Yeah, the reaction time is faster. So that would be a one-tailed test because we just are looking at just faster. But if we're looking at something like, I don't know, do different groups of people spend a different amount of money? So like people in like Oregon and people in Washington, people in California or whatever, right? Like if you compare those people, do they spend a different amount of money, right? Well, we don't know which one's which. You might just want to say, is there a difference between these two groups? And you would just look at a two-tailed test in that way, because you're just saying, oh, there is a difference. It's not equal to each other. Okay. So just know that it's kind of like the deviation, the split right here. There's one tail and then there's two tail. Okay. Any questions on that one tail, two tail, and how this goes through? Okay. And just, I didn't really say it, but this red line, the way it's determined is that alpha value. It's like, basically that is what's determining it if it's going over here. Okay. And note this is all normalized to 1. So you can imagine that's what's going over here, is that this is a value of 0.05 usually. Okay. Cool. All right. And this is where I talk about p-value real quick. This is all the review stuff. So, but I talk about the p-value puppies, which is this, I can't see if it's the article or something else. It is the article. Okay. There's a video in there. I bet the link's somewhere in that article if you're looking for it. Essentially how weird it is. Basically, here's the kind of like the same exact looking thing. You can see observed value right here. You can see right here in this blue is saying like what the weirdness zone, saying like, you know, how weird are we allowed to accept it? Our alpha value determines like this line right here, determine this part. These are, like you said, very unlikely. And then this is basically saying, okay, like what is the observed p-value? So essentially like what is the p-value from this observed point versus like, are we allowing us to actually make a significant change? Okay, cool. And I mentioned p-hacking, like I said before, is that you can retest essentially. So if you get something that's relatively small, you can, oh, actually I don't think I mentioned this. So one thing that can happen is, let's say you get something that's slightly off significance, like on the edge of significance, 0.06, right? Now, there's a chance that like, okay, there isn't a real effect, right? But it's so close there, right? Maybe it's just you need more like participants, right? So if you had more participants, that's a better result test, more accurate, right? So maybe that can tell us what, if our, what's it called? Our p-value is like, you know, maybe if we get more people, we can be more certain. Say, oh, it is not significant, or maybe it is significant. Maybe we're just kind of like, we're just unlucky side, right? So one classic thing you might do is add more people if you get this value. As you can probably tell from my tone, that's not a good idea, right? And the reason why is, it turns out, is that you only will do this if you already are close to getting significant. You probably are going to retest when you are not significant and you want significance, right? Versus if you got a p-value that's over like, let's say equivalent like 0.04, you probably aren't going to retest it because you got the significant value. You're like, cool, there's evidence. I can reject the null hypothesis now. So that's one step reason why you shouldn't do this way, okay? The other problem is that by adding more people, even though more people will be useful, there's still a pretty high chance by adding more people that you're just going to pick more people on the edge, and it'll put you even further away from this point. So maybe it's not really significant. It really should show that there's no difference. So we fail to reject the null hypothesis. But by adding more people that are more on the extreme end, that are just by pure chance, that you might actually end up pulling this part. So you can think of it as that 99%, or sorry, outside of that one standard deviation, you have 1/3 of the time you will pull people out on the extreme ends of that distribution. So the problem is that you're going to, by adding, you know, 1, 2, you know, even more people, you are more like, you have a not a non-zero chance of pulling more people who are actually less like the true population and get a significant result when one doesn't really exist. So this can be a big deal. Okay, so that's kind of like one way to do p-hacking by accident, essentially. Like, I don't think most people try to do this necessarily on purpose. You think, oh, I need more people, and you pull more people in, and it turns out that's the opposite. Okay, I mentioned about basically this article, or this little drawing right here. I won't repeat that. The one sample z-test, I'm not going to go for this whole part right here, because we're going to go right into t-test, which is basically going to overwrite our z-test. Our z-test, just so you know, assumes a normal distribution, but that's not always going to be true. So we actually tend to not even use a z-test ever, like in practical like applications. We'll probably always use a t-test by itself. Okay, but I will mention Jeff, another instructor, has what's it called, a walkthrough for a z-test. I think does a really great job. So this is a little video that I think I'd say check this out if you wanted to see a little walkthrough of what a z-test looks like. Okay, cool. All right, I wanted to show this before, but I guess it was missing from my thing because it was untitled. Okay, so any questions though, reviewing any of these parts? I think now hopefully you guys have seen it a few different ways now, a few different times. Okay, so I'm going to move over to effect size, which is kind of leading into.
Victor,
Oh, yeah.
sorry, I didn't hit the button fast enough. So the Z, like we typically use t-tests, not z-tests. Do we just like why do we like when would we use a z-test? Like, I mean, I guess I could watch the video too if that.
Yeah, you would use a z-test mostly if you can already assume the distribution is normal from the sample. And it turns out you can't really assume that when you think about that. And that's where we use a t-test. Basically, the t-test will use a modified normal curve, and that will be a little more accurate. And then going on top of that, we'll talk about the student's t-tests. And then student's t-test also relies on the fact that the variance is equal amongst the population sample. And we can't always assume that sometimes. So we might do a Welch's t-test. But essentially the concept of figuring out we call it the test statistic, like the z-test, or sorry, the z statistic, the t statistic, and so on. Whatever statistic thing we have, we use that and compare it to the p-value. And essentially it's the same process going through. Okay.
Thanks.
No problem. Okay, so effect size. So let's go through here. All right, so with effect size, we're going to talk about a few ways. We'll focus on Cohen's D statistic. Note that there's other ways you can measure effect size, but we're going to talk about that one specifically since that's the one that's focused on the curriculum. But no, there's plenty of other ones you could use. Basically, the effect size is kind of like in, not contrast, but in like in addition to the, what's it called? The p-value, right? To see if something's significant or not. So the effect size is basically saying, was there a significant difference? So I think I mentioned about like the elephant seals and like dogs, stuff like that, saying like, okay, like what's the huge effect size? This is really useful when it's used in meta-analyses. So in the meta-analysis, we kind of mentioned a little bit, Jenny mentioned a little bit too, is basically you're using multiple studies and you're aggregating them together and combining essentially the results together and seeing not just about like, was it significant, but also what was that actual effect? Turns out for a lot of those things, like I think that's why I suggest checking out Healthcare Triage, because he does a great job of talking about meta-analyses in general. There's a lot of things that we kind of consider are true in like health-wise and stuff like that, that you realize that when you do a meta-analysis on the studies that were performed on it, they don't necessarily hold up to scrutiny. You find out that the effect size is relatively small, and then you realize like, oh, wait, like, and then even then, sometimes the effect size is like non-existent or in the opposite direction. A classic one that I think Healthcare Triage loves to talk about, like Aaron Carroll really likes coffee. And he hasn't really liked coffee, but he likes coffee, and he always gets a bunch of flack for drinking coffee and how like it's unhealthy for you. And he basically does this whole meta-analysis, like talks about the different meta-analyses of these things, and basically showing that when you do this stuff, you find that basically there's very little effect on everything that you look at. And usually, in some of the cases, they're actually in the opposite direction of being like, oh, this seems to be suggesting it might even be slightly good for you by drinking like one of the studies basically said if you drank between 5 to 7 cups of coffee, you tended to have a better blood pressure than people who drank no coffee. It wasn't until you drank over 7 cups of coffee a day that you saw a negative effect. And he talks about, like, it technically shows that there's a positive thing, but even then, it's like that positive probably doesn't really exist. But in most cases, if we saw that in like the media, if there's a slight positive correlation, you'd be like, oh, cool, like that means it's super healthy for you. Like you should drink this all the time. So in reality, it's like, oh, it probably at the worst has no effect on your health. So kind of an interesting thing. Talks about something like breakfast. Breakfast not being like actually really important. Interestingly enough, I don't know if you guys have seen those studies. Do you guys know what I'm talking about? Like with breakfast, I hope I'm not like gonna ruffle anyone's feathers. Okay, so
I've heard stuff like that.
Yeah, so first of all, who's been told breakfast is the most important meal of the day? Right, everyone, right? I was told that. I was tricked into this too as well, right? Breakfast when you look at the studies, it's really interesting. So one study that everyone loves to talk about is school children and eating breakfast, right? Is that if you eat breakfast in the morning, you're more likely to do better in school, right? They see test scores. There's a study that shows your test scores went up when you gave them breakfast. However, if you look at the study closely, the students were not from an area that might be more, I guess impoverished might be the right word for it, but like they didn't have as much resources available. So there were some students possibly not even getting food to begin with. And so it's not that necessarily breakfast helped them out specifically. It was that they weren't eating at all, like, or they weren't eating as much as they probably should have been. So basically they were already hungry, like more than just breakfast. So by giving them breakfast, they weren't as hungry, so they were able to perform better. But when they basically standardize an meta-analysis and you try this with social economical groups and say, okay, these students from these different groups, those ones you find that breakfast doesn't have a significant effect on their results. So these are kind of things where effect size, can be really important to say, okay, like, well, how much of an effect was it? And also, collecting these together, was the effect size collectively actually an effective thing, or was it something that's very specific to that one group? In that case, you're like, oh, there's something special about that one group, which is the reason why you saw an effect. So anyway, I'm not going to ramble too much about breakfast and everything like that, but yeah. And again, health, I'm like, I don't know why I'm like pushing this so much, but like I really like the his approach and stuff like that. And then of course you can always draw your own conclusions and look at the studies themselves too. So I think it's a good practice. Anyway, effect size. So one thing we can talk about is basically saying like an effect, basically like these are both significantly different, statistically significant different distributions. So this is from the curriculum itself, is that we have a purple or I don't know, magenta-ish, right? And a blue one right here. And these are two different groups. So you can think that there is a difference between these two different groups. This also might also show their significance between these two. The thing about this though, is that the effect size, as you can tell, this is a much larger effect than this very small effect, right? So we can actually think of this in this part, it's like, okay, like the problem is that if you get some value down here, you might accidentally misclassify this as pink over here, even though it's blue. But that's a very, very small amount of people that you do that. However, over here, you can see that because the effect size is so small, right, that there's a chance that there's a pretty good chance that someone who is in blue here, that's over on this side, will be misclassified as maybe pink when it really should be blue. So we can actually calculate this misclassification rate. So you can think of this, I guess you could think of this either true positives or false positives, depending on which ones you think is positive. But this basically relies on the fact that there's sigma 1, sigma 2, meaning that basically the standard deviation of each one times, basically, this is a way to formalize essentially with the, what's it, the standard deviation, not the standard deviation, the mean of distribution 1, distribution 2. This exact formula, do you need to memorize this? No. Like, you don't need to like memorize these things and like, oh, like you need to put this out. You don't even have to necessarily know exactly what's going on here, but you can see some relationships. And the reason why I show this equation is to say, okay, like basically depends on how big the means are. So if the means are very, very different from each other, right? Okay, you're going to have a big effect or a very small overlap. And then we can see actually the standard deviation. If the distribution groups they're very, very skinny, so we have the same exact difference, but the distribution is very, very small, a small standard deviation, you won't have as much crossover versus if you have a very large, standard deviation, you would have a lot more crossover. Okay, so I just wanted to kind of show this equation to see how that relates in there. But anyway, there's also a mention about the probability.
Victor,
oh yeah, good.
If you have a larger effect, it's easier to misclassify. And a smaller effect, it's harder to misclassify. Is that the correlation?
Opposite, I think. Is
opposite.
If you have a small effect, like this is essentially a small effect, you're more likely to misclassify between. There's more overlap.
Okay.
Yeah.
Great.
So it's kind of like if I have, no problem. It's like, for example, if I have like a value of 0 right here, in this kind of group, I know almost for certainty, like it's going to be in the pink group. But if I have a 0 over here, well, it might be in the pink, it might be in the blue, I'm not sure which. Same thing even for like -2 or like -1. It's like most of them will be pink, but you can see that some of them will be blue classified as well. Okay. Cool. All right. And then moving to probability of superiority. Basically, you can think of this is that this is another way. This is gone more in the curriculum, so I'm not going to go full into this, but it's another way to check, what is this effect going through? You randomly pick a member from each of the two populations and compare them. And so you can do this over and over, basically randomly picking them and seeing if there's a difference between the two. And you can use the sample of unequal sizes to basically determine the portion probability. So I'm not going to go through this because the curriculum shows like kind of a little lab of going how to do this. But the point here is that you can essentially see what that overlap is by randomly picking out and seeing if there's a difference between those two. Okay. Cool. So those are two parts. The one that you'll probably most commonly see and like most commonly use is actually Cohen's d statistic. So for Cohen's d statistic, again, I'm more like showing you these parts to just kind of show you where these numbers come from versus just like telling you it, but know that you don't have to memorize those parts. So note that here, this is our pooled variance, and so pooled variance basically meaning that you're scaled by how many members there are in each group. So remember, distribution 1, distribution 2, that's what we're talking about, 1 and 2. So basically it's saying, okay, we have this pooled variance, right, the sigma squared, and this is basically based on this n1 and sigma, or I should say like the variance 1, right? And so note that this is basically to take into account that if there's many people on one distribution or many points in one distribution, we're taking into that account. So that way, you know that if you have many people, well, you know that there are going to be some people that are going to be way off to the side, right? So that's why we're taking this into account. And by taking into account of how many there are, and then combining those variances together, we can actually say, okay, what's the difference between mu1, mu2, right? And then say, what is essentially that sigma pooled? And this creates a metric essentially called Cohen's d statistic. So this Cohen's d basically allows us to say, okay, is there a small effect? Is there a large effect? All this, and it's more standardized. So that way we don't have to worry about units. We don't have to worry about like, oh, is it 3 pounds? Is it 2 pounds? We can quickly look in comparison between the two different groups saying, oh, this has a small effect, but this one has a big effect and such. So these are more rule of thumbs, like I said here. You can get a number here. You will see numbers directly quoted, but the point is like there's not a firm like what is a big effect, what is a small effect. It's all in context, right? A small effect and something like, like, I don't know, like a small effect in like number of dollars or something like that for the country. If it's a very small effect, it doesn't really matter very much. But a small effect in like, let's say a medium effect for something like a life-saving drug, well, that might be worth the sense of like, it's a very small effect or it's a very medium effect. That might be something worth doing for something that's like really important. So again, context is something that matters. A large effect, right? If I have like a very large effect here, it might make sense. Like, okay, we were only going to do this thing. Like it's going to take a lot of effort to, let's say, here's an example. If we change the website to red to blue, right? And that gives us more people on board. Well, let's say it takes a lot of effort for us to actually like code it in, deploy out in the fact that it's going to be red versus blue and stuff like that. And we find it has a medium effect. It might not be worth the amount of time and effort and money of bringing in new people, even if there is a medium effect. It might need to be a large effect in order to be cost effective. So those are things to consider when you look at this D statistic. Okay, does that make sense to everyone? Cool. All right, any questions on like what this D statistic is measuring? No, okay. And again, it's basically a way to normalize, not normalize, that's not, I don't want to use that word. It's a way to make it non-unit, right? It's basically, there's no units tied to this D statistic. Okay, cool. All right, so kind of bringing this all together, we can try out some code, right? Hey, remember code? It's been a while. All right, so we can actually get some parts. I'll use SciPy. You'll notice that I'll tend to use SciPy more than stats models. So just kind of know there's a difference. Yeah, I think the curriculum tends to be a little more on the stats models than SciPy for statistics. But I don't know, I find SciPy useful. So anyway, so one thing we can do is actually create a PDF, right, from a certain value. So I think this is actually from the curriculum itself. I might have made a few changes and stuff like this, but just know that we're basically making our PDF from this point. And so I'm just gonna run this guy. Also kind of just to go through here, since in the curriculum, I'm not gonna spend too much time. Basically, we're checking out the overlap of superiority, and then we're actually creating a function to plot out these functions, right? So we can go back to them if we're kind of confused on like what's going on. But now we have this part, if you can actually check out, it's like, okay, we can graph out these different plots with a Cohen effect, a Cohen's D with 0.2. So now with the 0.2, you can see is that this right here is showing an overlap of 1.085, right? Superiority of 0.41. So you can basically start comparing these. But the main thing is I would say, look at this visualization. You can see a Cohen's D effect of 0.2 with these values. It's relatively small. It's very difficult to like this might be something like you can see, okay, there would be a huge misclassification here. Okay, versus a Cohen's effect or Cohen's D of 1, you can see now we have actually a bigger effect here. And note that there's still quite a bit of overlap, right? Just because we say like Cohen's D is like a medium effect, that's still pretty decent, right? Like there's a still decent amount of overlap going through. But there is definitely a difference between these two, and that might be something that's important for whatever context. I went to the extreme here, just Cohen's, well, I'll show Cohen's D like 1, right? So you can see Cohen's D of 1, we get this value right here. So you can see it's not that much different. Oh wait, this is 0.5. That's weird. I wonder if this is in my code. Oh wait, am I thinking of this wrong? Oh, okay, that's a different value. Sorry, I was thinking this was printing out Cohen's D. It's not. I think that's printing out the overlap security. I'm not sure what that is. Anyway, let's try like something like 4. You can see there's a very large effect between these two, basically no overlap between the two. In this case, like something like this, it likely means that you probably don't even have to do this test to see the difference between these two. In all likelihood, you likely will get Cohen's D that are much smaller than, not much smaller, but like probably smaller than 1, unless it's very significant. But this will help you figure out, like, okay, this is like the difference between these different groups. Okay.
Victor, what are the units on overlap?
Oh, this guy right here?
Yeah, what is it? What's this number?
There aren't any units. Funny enough. Well, let's check out the equation, right? So like, if you look at the overlap right here, is this what we're talking about? Yes, okay. So we're talking about this value right here. Is that, I guess I guess I take it back. It does have units in a way. It would have units of whatever that mu is right here. But because our variance, ooh, now I'm taking it back. I don't know.
Yeah, when I worked through this, it kind of seemed like in the examples, it kind of seemed like overlap was a fraction, like they overlap by 30% or something. But then I also noticed that the solution for that lab has overlaps over 1, and you're getting overlaps over 1 right now.
Yeah, I would say it's not a percent. That might be something. If you know where in the curriculum that's sent, you should send that over so that I can check that out. But I wouldn't say it's a percent. It's much more. The problem is that, how do I say this? It's the area underneath this curve here. So it should in principle be like under 100%, right? But if this is not scaled like to 1, then you're going to have some issues where it's not going to add up to 1. That's my guess. So that's why like I'm hesitant to say like it really shouldn't have units, but if they weren't scaled, this will essentially end up having units of whatever mu is, essentially whatever the mean is being measured in. So you could technically get something that's above 1. But for example, the D statistic, this shouldn't be getting a specific like value by itself. Again, this is assuming that we actually have it scaled over from here. So, and that's why you'll see no units actually used for the D statistic. Okay. Sometimes I think, I don't know. I come from a background where all we talk about is units, and like it's sometimes one of those things where I think sometimes other fields don't do that, and it's implicit. So yeah, hopefully that kind of makes more sense. But good question. Yeah. But for the most part, the D statistic is the main thing that we'd be looking at itself. And then I don't see too much talk about overlap specified by itself. Usually I see it more, D statistic is the thing that's quoted, and talking about like the type 1 and type 2 errors. Okay. Cool. Which I realized I didn't actually mention about type 1, type 2 errors. I don't actually know if I have that within here. I think I do talk about it a little bit later within next time and everything. Types of errors. We'll talk, get some time. Sound good? I don't think it's that long. So If not, let me just take a quick peek. I can't remember how long it is. No, we're going to save this until next time. All right. That way I don't overload your guys' brain. I know it's been almost 2 hours, right, since we did this. But type 1 and type 2 errors, just basically know it's false positives and false negatives, right? That's what we're talking about. And we'll talk about how that goes into. I never really see overlap or even probability of superiority. Maybe more statisticians use it. I don't know. I'm not a statistician PhD, so I wouldn't be able to really like tell you. But sometimes, I mean, I love statisticians. I want to make that really clear. But sometimes I think when you get really deep in your field, sometimes you think that the really, really minor things are really, really important. And they are important, but usually you can kind of skip by them. Kind of fun. We have a few minutes, so I'm kind of done here. So I just want a little quick story time, right? So like my background's physics. Like I like to emphasize.
Go because I have to
Okay.
go to the airport. But
Actually, I'll go stop recording here too. So okay, they don't have to hear my stories.
Bye everyone.
Bye, Lauren.